Right. Thanks, everybody. So indeed, this is our research area here, history mathematics. We have a little group, and let's see if if we can convince people of the value of that. It has much to teach us still, lessons for us all. So the Greeks had these classical construction problems. You've heard of them: double the cube, trisect the angle, square the circle. The Greeks were obsessed. I put here a long list of all the preserved solutions to these chronological order here, the solutions that the Greeks offered. So 24 or so solutions. Over and over again, they insisted on these things, doubling the cube 12 times and so on. But it seems quite obsessive. Why were they so manic about this? You know, apparently they sat around and one day then told themselves, oh, you know, let's make a cube twice as big as another cube. And everybody's like, oh shit, yes, you know, let's do that for like 12 times over. It's the coolest thing ever. Strange, isn't it? Why would they react this way? They seem that, what a strange attitude. You know, there was other stuff going on, right? You think that maybe there were some broader perspectives. You might want to pay attention to something in the broaden your horizons a little bit after you have already doubled the cube 12 times. Maybe turn to something else, or no, keep doubling that cube over and over for hundreds of years. They are very persistent, and they are, you know, somebody's got to think of the cubes, right? These cubes aren't going to double themselves, right? So these people are obsessively sitting around doubling cubes. Very peculiar behavior. So we have to explain that why these people were so obsessed with these problems. Of course, today you have this sort of, everybody knows that, oh, these problems are actually impossible, you see, and you have Galois theory, and we are so smart, and they were a little bit dumb back then. They didn't understand yet that they were impossible because they didn't have algebra like us, Galois theory and groups and stuff. So that's why they failed, and we are the best. You know, that's a mistaken impression, of course. In fact, the Greeks knew that these problems are impossible. That's, in fact, presupposed by the Greek geometers that, of course, it is impossible to solve these problems by ruler and compass. And that's why they proposed other solutions using other methods, because they took for granted that, of course, everybody knows that they're unsolvable by ruler and compass. So, in fact, they regarded the impossibility result that we are so proud of today as rather boring. To prove that they're unsolvable ruler and compass is okay, fine, but you know, that's not really the point. Today we are overly pleased with ourselves for being able to prove that, maybe. Whereas what they were really interested in, the Greeks, were the constructive foundations of geometry. Constructivism today, nobody cares anymore about that, but to them this was the real deal, the heart of the matter, you know, the constructive business. Founding geometry on constructions. This is what I claim, and this is why they were so obsessed with these problems. Because if you want to found geometry on construction, and you want to give a constructive foundation of all the mathematics, you already Euclid did a good job, you know, with his ruler and compass, and that's a good start. There are some problems, though, that are not solvable by ruler and compass, and that's precisely why these problems were targeted or selected, because the real goal, you know, they didn't want to double a bunch of cubes. Nobody cares about doubling cubes. What they wanted was, we need new, broader, constructivist foundations of geometry altogether. These problems are just symbolic sort of encapsulations of what there really is, this research program to formulate the constructivist foundations of geometry overall. And these problems are just minor sort of symbols of that, what the real task, which is much broader than these individual problems, which nobody really cared about as such. But being able to solve these problems that go beyond ruler and compass entails being able to give an extended constructivist basis for geometry altogether, and that's the real goal, and not trisecting the angle, which is whatever, you know, who cares. But the methods that you need to be able to trisect the angle, those methods need to be some kind of potential foundations for geometry, general methods, and that's what you need. That's what we're after. That's the real goal of this stuff. So, and the solution methods then that the Greek guys proposed, which are all non-ruler and compass methods, what kind of thing? I mean, many of them are quite physical. They are involved sort of machines or linkages, different sort of rulers that are interlocked and pushing each other, tracing curves in various ways. There are a bunch of those types of solutions. We will look at some of this stuff in a few more detail later, but here I'm just kind of characterizing the broad types of solutions altogether that were available at that time. A lot of the similar methods of solution were based on these kinds of idea of sort of jiggling figures around. Like I take a ruler and I kind of move it around until it sort of clicks into a certain condition, or moving other kinds of figures like these triangles that Eratosthenes used to double the cube. You're sliding stuff around until certain things click into a collinearity condition, and then you have the doubling of the cube that you wanted, the side of a cube twice the volume of a unit cube. So this is so those types of solutions were apparently regarded as, one credible approach. Another approach is conic sections. They doubled a bunch of cubes, trisected a bunch of angles, or a general method for doubling any cube or trisecting any angle using conic sections. So that's apparently somehow you have solved the problem if you have expressed it as an intersection point of conic sections. Apparently, in what sense is that a solution? That's something we need to look at also in more detail. So now I'm just sketching the big picture here, and it's puzzling in what sense, for example, so some guy is saying, oh, I want to make an angle the third of another angle. And then people are like, oh, whoa, third of an angle, what a crazy concept, that's like very exotic, a challenging thing to grasp, and you have to give me a construction before I can understand what a third of an angle is. And then the guy is like, okay, let me explain a little more. I just do it like this. I take the arc that I need to trisect, I regard it as part of a unit circle like this, and then I draw this hyperbola over here, super complicated hyperbola, and then that's a third. That's exactly a third of the arc there. Oh, okay, good. What? In what way? What is this weird thing? You have a very simple problem, and you explain it in terms of some crazy complicated thing. In what? How is that supposed to be a solution to that? I mean, what exactly does it add? Does it clarify? Does it construct? In what sense is this a constructed thing? It is just a super complicated. It's very puzzling, isn't it? What does it even mean to solve a problem? If this counts as a solution, what are the standards of what it means to solve a problem then? How can you explain a very simple thing in terms of an extremely complicated thing? Why would that be good, right? It's very puzzling too. This is the mystery that we need to address. Here's another crazy method, the Arkitas method. Oh yeah, I need to double a cube, which is another way of saying I need to construct a cube root of 2. Oh, piece of cake. I just consider these three surfaces over here, you see? The cone, the cylinder, and the torus. I take their point of intersection, which is in here, whatever, some complicated point. And the horizontal distance from the origin there, boom, that's the length that I need. And now I have doubled the cube. Huh? Crazy. What is this stuff? It's like the guy was, suppose somebody says, oh, let this cube be twice as big as the other cube. You think that would be a kind of a simple step. Oh, no. That's a research problem, you see, to make a cube the size of another, double the other cube. Oh, that's a complicated research problem. You're going to have to explain it to how you do that. And then, however, in this course of the solution to that supposedly advanced problem, you are allowed to simply say, oh, let this thing here, super complicated three-dimensional curve, be the intersection of a torus and the cylinder. That's easy, by what kind of mysterious standard? You're not allowed to do this. You're not allowed to just say, let that be twice that. But you are allowed to say, let's take the intersection of this and this, which is crazy complicated. I had to do some hard work to get Mathematica to even plot this complicated three-dimensional thing here. And this triviality, that's a research challenge. But this extremely sophisticated, very advanced curve here, oh, no, nothing, they eat that for breakfast, What is the logic behind this? What are their priorities? What is it that makes this fine and that not fine? What kind of rules of the game are they playing by exactly where that makes sense? That's what I wonder. indeed, the written text that we have, you know, we don't have the original of Arkitas or many other people in the Greek time. We only have these later sort of summaries and stuff of their work. So it's not so reliable, but indeed the text, as far as we have it, does basically treat this complicated curve as sort of trivially given of sorts, you know. It's just saying, oh yeah, well, I have to take a cylinder and then I have a semicircle that's rotated. That is the generator of the torus here is generated by a rotating circle or semicircle, whatever. It will cut the cylindrical surface and will draw in it a certain line. Yeah, this intersection curve. Okay, you know, but that's somehow just, oh yeah, it will draw a line, piece of cake, right? So the text simply assumes that you can just take the intersection of surfaces at will, however you, even when they're very advanced curves. But it's perplexing. So this is treated as trivial somehow. And how can you then not regard the trisection of the angle as a trivial thing, where the double cube decides not a cube? Why isn't that trivial? If that's a trivial thing, then yeah. Mysteries abound. And now I'm going to explain why these things are not mysteries at all. And this is why. You know, when you introduce a new concept in mathematics, there are two ways of doing this. You know, you construct a thing. That is to say, you are only allowed to introduce new objects by saying, by object so-and-so, by figure a curve ABCD, I mean, the thing you get when you do this, you know, through an action is defined through a perform something that you create through operation, construction of the geometry themselves. The alternative way of introducing object would be to specify them by properties and say, you know, I'm considering an object such that this, for example, a cube that has the property that it's twice the volume of another cube. Then you have defined that is an introduction by property, basically a kind of a wish list to Santa Claus. You know, it's very you cannot create mathematics that way by wishful thinking. You have to create it by making it. So because it has to do with philosophy of mathematics, and it is connected to questions of consistency. Construction is a way to ensure consistency, whereas introducing objects by fiat, by defining through property, by a wish list to Santa Claus, those kinds of objects can easily be inconsistent, incoherent, and lead to contradiction. And this is what the Greeks were highly aware of, and this is why this is going to make sense of this division. You know, this is why it's so important to construct the double cube, why it's so important to intersect an angle, and so on. It's because you have to reduce all geometry to this stuff. This is what my claim. You know, of course, Euclid is very constructivist. You know, his very first proposition is how to make an equilateral triangle. And so he has step by step using ruler and compass. He's able to construct an equilateral triangle like this. He is really a guy with the toolbox at hand, you know, Euclid. A square, for instance. Of course, Euclid shows how to construct a square. He doesn't just say, oh, let ABCD be a square. Oh, God, no, that's not permitted. That's this letters to Santa Claus way of introducing a square. No way, that's not going to fly. You have to make it. Okay, first I do it, and then I do that, and then I do the parallel, and then I do. Of course, these are all previous constructions, how to make a right angle, how to make a parallel, and all that stuff. He has already explained that with ruler and compass before. And so all of that stuff Euclid has spelled out in great detail, how to make the thing. He never has any theorem about a square before he has made a square, of course. You may know that the proposition 47 is the Pythagorean theorem, which is about squares. So of course, before he has his first theorem about squares, he immediately before that, he shows how to make squares. Otherwise, you're not permitted to talk about squares if you have not shown how to construct them. So indeed, we can see how these constructed objects that Euclid had taken such care to construct that entails that they are consistent and not in contradiction with not self-contradictory objects. However, if you were allowed to introduce objects by property, then you can easily end up with inconsistent object. For example, I was allowed to say, let ABCD be an equilateral triangle. This is permissible because of the construction. However, what this statement is almost the same, let ABCD be a triangle that has 3 right angles. This is a triangle with 3 equal sides, and this is a triangle with 3 right angles. Yeah, well, it's the same kind of thing. So if you were allowed to introduce that just verbally by saying, let ABCD be a triangle with 3 equal sides, you should also be able to, this is the same type of statement, let ABCD be a triangle that has a right angle and a right angle and another right angle, which is an inconsistent object, of course. It leads to contradiction and destroys all of mathematics, of course, at once. If you admit these paradoxical objects, you know, you're dead. Right? All of mathematics collapses like a house of cards. Right? So this is why it was so important not to, never to allow any objects to enter mathematical discourse in the form of a wish list to Santa Claus. That is to say, defined through let this be the case. Like let this cube be twice the other, let this be the third of an angle, you know. This is why these things are prohibited, in order to avoid these dangers. Or for example, let ABCD be a right triangle with these sides. Okay, that is inconsistent with the Pythagorean theorem, you know. Interestingly, in modern mathematics, you have very similar things like the Russell set, that you know leads to paradoxes. So it's here we have that danger again. If you're introducing things verbally, that stuff's gonna kill you, you know. Leads to inconsistency all over the place. In fact, this triangle that I mentioned, the right triangle with these sides, it's I didn't just invent it. It's from a textbook from 1522. It does use this example, you know. It treats it as if it, you know, it's just, here's one example of how you can calculate the areas of triangles. And let's consider this one, and it computes the area. And so the author is not aware, apparently, that this object is in fact incoherent and impossible. And it just treats it and applies formulas to it and does, you know.
Sorry, can I ask a question?
Yes, please.
Can you recognize what is written on the sides? This is some old German, maybe? Do you know what is written
German.
there?
Here is sieben, here is neun, that's 9, vier is 4.
Yeah. Okay, so it's like Dreieck also, and then Reim. Okay, thanks.
Diese ist 7 root, there's a unit of length, right? 7 whatever things long. Yeah. So yeah, or 7 things. Yeah. So these people, you know, that's what happens. You know, the great ancients, of course, were much more careful, and they would never make a mistake of this kind. But this is why they were so careful not to allow things like the double, the cube, the third of the angle without care, because then you might have walked right into a trap like this, which is not impossible. People have done. You know, so yeah, in fact, it's very important that the constructions are physical. Some people are like, oh yeah, construction, you know, it's like thing in mathematics. Look, it has to be a physical construction, a thing that takes place in reality, not mental, physical. It's an actual compass, metal compass, a wooden ruler. It's real. The materiality, very important. So it's not just a thought construction. Whatever is a thought construction anyway? Can you? Why can't you thought construct a thing with 3 right angles? You can just like, oh yeah, I imagine one of these, and I click onto one of those, and one of the, or I can imagine the length of 4 and 7 and 9, and I can imagine putting them together. You know, isn't that a thought? You know, the concept of thought construction is much too weak, too subjective, too unrigorous to sustain what we need. This idea about constructions being a warrant of consistency only works if construction has a seriously you know, by reducing it to physical reality, we are reducing it to non-subjective properties. We are taking the human element out of it, and we are ensuring that geometry is at least as consistent as physical reality, which has very strong, you know, support through experience, through well, if physical experience is not consistent, then we're all screwed anyway. So there are good reasons to reduce the foundations of mathematics to a physical, anchor it to a physical consistency, which is better than the sort of just intuitive ability of mathematicians to think that they have constructed something consistent. That is very dangerous. Oh, the great Brouwer said exactly this in his thesis, you know, great stuff. The language of Euclidean geometry owes its reliability to this only, that this, in fact, constructed independently, that it builds on things that are constructed independently of the language of the theory. So the thing is constructed, you know, in a sort of in a way that has objective sort of verifiability to it, other than just the mathematician just thinks it's consistent. We all know such mistakes can happen. And just as he says about Russell, and he could just as well have said about these other things, he said the problem with Russell's paradox occurs precisely because he's just doing verbal logic. It's just defining things through a word system, merely through a word like the wish list to Santa Claus, which is purely verbal. So there is no reason why it shouldn't contain contradictions. You have no guarantee that something that a mathematician has just thought up, that is supposed to be consistent. You have no warrant for that. Whereas if you ground it in physical reality, you do have a very strong independent grounds for not having to take the mathematician's word for it, but taking everybody's collective experience for it, that physical reality is consistent with physical experience. Here's another reason why it is very important to construct. So Euclid, like I said, he constructs a square. Obviously, ultimately, that falls back on his axioms. And so Euclid has 5 postulates in his theory. Those things about how lines and circles work and how parallels work. Those are enough to show that you can make squares then. But very importantly, if you assume only the first 4 postulates, and if you assume also that squares exist, you can from that derive the parallel postulate. So what this shows then is that assuming the existence of objects is very serious business. You can very easily if you go around thinking, oh, a square, come on, everybody knows a square exists. That's like, and every child knows about squares. I'm just going to let ABCD be a square. That's sort of an unproblematic thing to say in geometry. Well, no, if you take that kind of attitude, then it's impossible to do any kind of axiomatic treatment of geometry whatsoever, because then you have let the parallel postulates, a very sophisticated assumption about parallels, which is false in hyperbolic geometry and so on, very dangerous to just assume just like that. And if you have assumed the existence of squares, you have committed yourself to that without even being conscious, probably, if you just thought that the existence of squares was evident. So we see here that, well, if you're going to do axiomatic geometry in a serious way, you're going to have to seriously control how objects are introduced. And you certainly cannot take for granted that things like squares or something exist, because that will ruin the entire enterprise. For sure, hidden assumptions are going to proliferate through the entire system. So this I say is why you need to construct, because you need to, it's a matter of reducing geometry to physical operations, because it guarantees the consistency of the theory, or at least reduces the consistency to an empirical, trustable fact that physical experience is consistent. And protects against hidden assumptions, like in the square implying the parallel postulate. This is why the people constructed. Other people have proposed other theories for why the Greeks were interested in constructions. You might say, look, construction is about presenting the thing to the mind, sort of, explaining. In Euclid, of course, constructs the polyhedra, the dodecahedra and stuff, and things like that. You can say, okay, a construction of a dodecahedron, it's like a difficult concept to grasp, maybe a dodecahedron, or maybe then if you show the construction, it sort of helps the visualization process, or it somehow kind of assists the mind in, building up and thinking through mathematical objects. Clearly, that cannot be the reason why the constructive tradition of the trisecting the angle, doubling the cube, and so on. Obviously, it cannot have been for this reason, because, for instance, if you trisect an angle by this crazy method with the hyperbola, clearly that is not helpful. It's going to help me understand the concept, or visualize, or present to the mind the concept of the third of an angle. Obviously, that's crazy to do that with the help of this, which obviously a third of an angle is much easier to imagine directly than it is to imagine this supposed assistance to the imagination, which is way more complicated. So it doesn't make any sense. So clearly that's incoherent. And the same goes for many of the other solutions. Here we have another angle trisection. Same story. It's much easier to imagine the third of an angle directly than to imagine this elaborate convoluted construction that the Greeks have thought up. Existence proof, existence proof has maybe something to do with it. I prefer to think more in terms of consistency. In fact, the existence of the third of an angle or the double of a cube or a square equal to a circle in area, it's not really, from elementary continuity considerations, surely those things exist. And in fact, how do you know that this hyperbola exists? That is vastly more implausible or questionable assumption than to assume that the third of an angle exists, obviously. So that surely existence is not really do the trick here, since the things assumed in the course of proving it are much more questionable from an existence point of view than the thing constructed. Or the supposedly that these things can be applied, maybe they needed to trisect angles. Maybe they needed that for whatever, astronomy, cartography, whatever, some practical application. No, this is a total joke. These methods of construction are, of course, crazy, intricate theoretical things. It would be absolute madness for any practical person, like an engineer or a geographer or whatever, needs to trisect an angle, that they're going to use this crazy hyperbola or this elaborate contraption and start drawing these curves and taking intersection and then the third of that. Madness. It's way too elaborate, and way too the exactness of these procedures is going to be terrible. Obviously, if you wanted something that's good enough for practice, you will find other methods that are way better for producing quick and much more accurate practical results. For example, numerical. Of course, if, for example, doubling the cube corresponds to cube root extraction. Piece of cake to do numerically. Of course, the Greeks knew this. They knew how to extract cube roots numerically with arbitrary accuracy. It is an iterative algorithm. It's a recursive thing. You just keep going, and as good as it gets, soon you have way better accuracy than you could ever achieve with this completely preposterous physical construction. So clearly that cannot have been the reason. But this is the reason. From this point of view, it makes sense. Their peculiar obsession with construction, it does make sense from that point of view. At least many of the things make sense that way. So a lot of these things are physical contraptions that produce the object. So, from the point of view of we need to make it in order to sort of anchor it in physicality, then from that point of view, it does make sense, these solutions. Still, though, there are some perhaps gaps in here. So here I have summarized all the possible methods, and I have pointed out that many of them are obviously physical in nature already. So these ones, for example, clearly physical. The sources are very explicit about this. Eratosthenes is talking about these triangles. They are made of bronze, and they are placed in a wooden box with grooves. And so the way he describes it is absolutely 100% physical. Certainly not like an abstract story about triangles, but it's definitely physical triangles that are being pushed around until they align. And so, and this other stuff, there are these rulers that are sort of interlinked in certain ways, and they're pushing each other, and they're making a pen move, and it makes a curve. And this guy is also very physical. The sources are like, well, I put the nail in there, and I put this knob in this hole in the ruler, and that's how it's definitely physical, 100%. And then there are a lot of these that are not necessarily explicitly physical, but nevertheless, you can clearly interpret them physically. Like Euclid never says, oh, by the way, when I'm talking about lines and circles, I mean, they're made by these physical tools, the ruler and the compass. He never says this, but you can understand. It's obviously very easy to interpret it that way. And the same with certain other things, like this stuff about the marked ruler sliding into position. And so this is very, very readily interpreted in physical terms. Surely that's what the intent was. So we start to get this explanatory model that it's about anchoring it in physical construction. It works for almost all of these things. Maybe the ones that work least well are the two that I already highlighted as the most puzzling, maybe. The Arkitus thing with the surfaces and the conics. In what sense are those really physical, though? This is a weird stuff about surfaces cutting each other. Is that really a constructivist reduction? In what sense? So maybe mysteries remain here. So those are the mysteries that I will solve. Look, the Arkitus cube duplication, then this stuff that we mentioned, it's not this is not at all how to read it, what he originally said. Of course, if you put it this way, then it doesn't really fit my story. That is not really a physical making kind of thing. It is more of a, yeah, let this thing be and let that be and let that be the intersection. This is more of a wish list of Santa Claus type of construction, the way it stands. But here's what he meant. I have reconstructed what Arkitus meant, and he meant the following. It is not, there are no actual cones or toruses or cylinders involved in this construction. There are only certain curves and lines moving around, and okay, this thing here is like say the door of a door, and this is like the hinge end of the door. The z-axis is where the door is attached there to the z-axis. And now I'm gonna move this door here, open the door gradually. That's what's happening in these slides. And as the door opens, it pushes these other parts. For instance, you have this stick sticking out here, which is sitting on the the forefront of the. It's placed against the door, and it's also locked at a 60-degree angle to the to this axis. So when the door is opening, it's going to keep pushing that line. It's going to move down, right? Because this guy is going to remain. This line is going to remain touching the door, and it's going to remain locked to 60 degrees to the axis by some mechanical whatever thing attached to it. So that means that as the door is gradually opening, this guy is moving along the surface of the door there because it's being pushed by the force of the door. And that, in fact, that's what he means by a cone. It's really just a line that is moving around an axis like that, and that is with a fixed point here, and so it generates a cone. And it's the same with the other parts. So here I have another stick standing up from the ground like a flagpole or something, and that's also being pushed by the door, of course. So it's moving along with the door here. But it is also constrained here in the floor. There is a circular sort of rail that's like a toy train track rail or something, so that this guy can only move along that track. So when the door is pushing him, it's moving with the door, but it's also keeping within the sort of groove that is cut in the floor there. So that corresponds to a cylinder then. If you take that guy and push it all the way around, it's a cylinder. And then the torus comes from this semicircle drawn on the door here. When you push the guy, open the door all the way, that guy is gonna trace a path that is a torus. And in fact, you don't even need a torus as a whole. You only need this radius of that semicircle, which also is constrained to move here. When the other parts move, this guy is going to become pushed around, and so eventually these guys lock into a certain position. You can't open the door any further here because this guy needs to go in and this guy needs to go down, so they're sort of in conflict and they're locked. You have, and that's in the locking position, you have the duplication of the cube. It's this elementary thing. So in this way, it is a physical construction. It is a device. It's sort of like ruler and compass. You have a device and you say, now I apply this force and it moves and it gets the thing that I need. So this is what I believe the Arkitas originally meant. And from this point of view, it is consistent with this story about the mechanical generation and constructivist foundation type of thing, because he is truly exhibiting the thing in terms of physically testable, groundable operations. So, okay, I managed to reconcile the Arkitus thing with the constructivist interpretation. Now, what about the conics? They also do not seem to fit the constructivist interpretation. In what sense is this? Are these complicated curves sort of constructively given? By what logic? How can they just be called upon and assumed as given? Well, that seems contradictory or difficult to explain. And yeah, like I said, we taking care of the Arkitus one now, and now this is the only mystery left, as it were, the conics. that doesn't fit the pattern of the others, why would the conics be so different from all the others? You know, almost all the possible solution methods are always about some mechanical device or other, even the Arkitas in the meantime, if we accept this reconstruction. So it's like everybody thought that the right way to construct a double of a cube, a third of an angle, was with some mechanical contraption, some physical instrument or machine, except the conics. Well, they are apparently completely abstract, given by whatever, some equation or something. So that's crazy. Why would the conics be so different than everything else? Why would they play by the separate set of rules, you know? So they don't. Conics are also constructed by machines. This is my claim. The conic compass is the tool for generating, which is a tool that fits exactly in this tradition. It is an ordinary compass with the addition that the pen arm has variable length. Like, for example, the pen is contained in a cylinder so that it can slide up and down, however high it needs to go in order to reach the plane here. There's a horizontal plane here, the piece of paper that you're drawing on. It's the distance is changes as you turn the thing. So if you had a normal compass here with one, you have the axis arm and the pen arm, just like a normal compass. But if you, with a normal compass, you can't draw like a parabola or something, because if you try to spin it around this axis, you would miss the paper. But now that you can let the pen slide as needed, and then you can you have this generalized compass that has the axis arm just like a normal compass, that's this fixed axis, and then you have the pen arm that is the thing that adjusts its lengths as needed. In fact, you can say, so this is a plausible theory that maybe that certainly gives an instrument way of generating conics that makes the conics fit the tradition of the other instruments. But you can say it's actually almost entailed by the definition of a cone anyway. You know, so people define the cones. Euclid's definition of a cone is the rotation of a line around a fixed line, an axis. So what is a cone? It is a line moving around an axis, which is literally what this thing is doing. So you might say, in fact, it's not so far-fetched to think that the Greeks thought of it this way. It's almost just entailed by the definition of a cone, a thing spinning around a thing and then cutting it with a plane. So really, you can immediately adapt this definition of a cone into the idea of the conic compass. It's just trivially sort of entailed immediately by the thing. So a fixed axis and a spinning thing. So we know that we don't know if there's no documentary evidence that the Greeks did this stuff, but we know that it was done not so long after. In the Arabic tradition, you have this conic compass is documented, and here's Leonardo da Vinci drew one, and so on. Very interestingly, the conic compass, this is something I had to check as well for my theory, that the conic compass can in fact be used to generate the conics that are used in all the conics that I showed in my previous slides that are used for trisecting the angle, for doubling the cube. All of those conics can be produced with the conic compass with quite simple choices of parameters. So here I'm showing how you could do that, how you need to set up the conic compass to make it happen, you know, how to position the A and this point and the height, how to calibrate the compass to draw the thing. And all of it's very important that everything in this table here are ruler and compass constructible things. So with ruler and compass, you can take square roots, and you can do the 4 arithmetical operations, addition, multiplication, and so on. So that is to say, the calibration of the compass doesn't need anything other than Euclidean operations, ruler and compass operations. So of course it would be circular reasoning if you needed the cube root in here somewhere, because you need to, the whole point of drawing the guys was to make the cube root, for example, for the cube duplication. So, but it's not circular because it used from it. Here's another theory. Not everybody accepts, of course, that the Greeks used the conic compass. In fact, almost nobody, but of course, that's what I argue. So another alternative would be maybe they thought of conic sections as given by, basically by their equations, which entails a pointwise construction. So the Greeks knew perfectly well that, for example, the equation of parabola can be written like this. They didn't use this notation, of course. They didn't have coordinate system and x's and y's, but they said the same thing in terms of areas like this, which is comes to the same thing. There's no, doesn't really make a difference. So this entails immediately that you can easily plot the parabola pointwise, but pick some x value, find the corresponding y thing, and put the perpendicular and the y coordinate. So pick another x value, pick another x value, and so on. So you can, certainly it's possible that they might have regarded the parabola as given in that way by saying, choose a bunch of x values, construct the corresponding y things, and plot the curve point by point. Yes, that can be done. And so they did, of course, they knew about these equations for the hyperbola. They have a beautiful standard form like this. It's very neat stuff. For the ellipse, it's very similar standard form, sort of symmetrical with the other, but with the minus sign. So, okay, well, that was known. In fact, some people think this is what they did. So the famous Stanford professor, Wilbur Nor, thinks that, yes, Manic, who was the originator of conic section theory in Greek antiquity, we don't have his work anymore. We're only left to speculate what he might have favored, which method of construction or whatever. But according to Wilbur Nor, then he used a pointwise construction, just like basically plotting the equation. With all due respect, no, he did not. No way in hell that he used a pointwise construction. That's crazy. In fact, why pointwise constructions are so bad is not understood today by Stanford professors, but it is understood by the great classical masters, like, for instance, Christian Huygens, the great national hero. He knew exactly why the pointwise construction is total nonsense. And here he explains it. Well, the description of a curve through points cannot be regarded as geometrical or complete. Such lines described in that manner cannot serve for a geometrical construction for certain problems because, in my opinion, the only things that can serve this purpose are those that are constructed through some instrument, such as the circle by a compass, or the conic sections or the conchoids through instruments invented there too. Yeah, exactly. He said this guy gets it. It's all about the instruments that you need to draw the thing. Instruments for drawing conics is the essential reason why conic sections are legitimate objects in mathematics, because the lines that you have drawn from point to point, that is to say, if you have plotted, for example, these curves here, if you have plotted them by plugging in x values and plotting a bunch of y values, and then you connect them by hand, you have lots of points and you kind of extrapolate the curve from many points. If you do that, then you can only come close to the sought quantity, like, for instance, the intersection point cube root of 2. This is the gezochte Quantität. You can only come close to those things, but you cannot find it according to geometrical perfection. Because what use is it to have so many points as you wish if you don't have the one point that you actually need, that you're actually looking for? This, Christian Huygens is exactly right. It's actually the idea of plotting the parabolas and hyperbolas pointwise is totally worthless, because you're plotting a bunch of useless points. You're plotting this point, that point, that point, that point. What use is that? As many as you like, they're all worthless. There's only one point you actually want, and that's the one you. If you're not constructing that, then all the other points are complete gibberish. So Christian Huygens is spot on about this, and he could teach Stanford professors of today a thing or two. But okay, so this is why it's so important to construct with the tool, with the instrument, just as Huygens says. So it's fun that, well, okay, maybe I should skip. I don't know how we're thinking about time here. Maybe I should skip my things, the remaining remarks, and see if people have some thoughts. I don't know. What is your philosophy about the timing of this? When am I supposed to be done?
We usually do 1 hour. You have a bit less than 50 minutes if you want to go with
You
that.
want me to speak for an hour? Yeah, of course, I'm happy to.
Well, no, it's up to you. You can do less or a little bit more.
Because, well, I think this is kind of a fun part. I guess these are my big philosophical points that I conveyed, but here are some fun historical dimensions of this, maybe kind of hidden truths, you know, in the original historical record for this. In fact, it's interesting that the name ellipse, parabola, hyperbola are introduced by Apollonius, which is quite late, you know, only the like very mature theory of conics are they called ellipse parabola. Earlier, for hundreds of years, people did a lot of conic section theory without those names. And at that time, they called the conic sections the sections of an acute angle cone or a right angle cone or an obtuse angle cone. So it's interesting. They assumed that the cutting plane is always perpendicular to the side of the cone. So you get different conic sections by changing the cone. It's the cone angle that is variable, and the plane stays the same. The plane stays perpendicular to the side. So they characterized the conic sections not in terms of the different planes, but in terms of different cones. And in fact, I claim that why would they do that? You know, isn't mathematics all about generality? And so, already the Greeks were obsessed with generality in mathematics. So it's a little weird that they sort of limited themselves to the perpendicularity, extremely peculiar, you know, of surprising that they will limit themselves. However, it does make sense from the point of view of the conic compass, because like I showed in my slide over there, how to configure the conic compass in order to trace specific curves with specific properties. You know, it needs to be exactly this parabola, not just some whatever parabola, but exactly that one. Then in order to do that, the best way is to start with the conic compass in this position, in the perpendicular position. This is the simplest. So you have a right angle here with, you can set up the parameters with respect to this right angle triangle. It's much easier than to consider the general position here, which is going to be super complicated to work with. So the idea of having the intersection plane be perpendicular to the kind of the vertex point of the conic, the drawing arm at the vertex of the conic, that it corresponds precisely to this, you know, that this guy here is this one, you know. So maybe they used this language, this language of conics that are referring to the variation of the cone angle rather than the variation of the cutting plane. That corresponds to the fact that they were thinking of the conics generated by this tool, so that you're varying the theta here. If you want the parabola, you make this theta 45 degrees, then you get the parabola. If it's less, then you get the, you know, if that's an acute angle, you get, and so on. So a right angle gives a parabola, so that's the total angle here. 2 theta would be 90 degrees, then you will get the parabola at one point at infinity. So this kind of stuff. So maybe this terminology has a hidden hint of its origins. By the way, this idea that I told you, a cone is defined as a line rotated about an axis. Well, yes, but actually Apollonius in his theory, that's how Euclid defines a cone. Then Apollonius in his theory of conics, you know, Apollonius is a generality snob, right? We all know those types of mathematicians who think they're so cool for making everything more general. And Apollonius was like that. He loved generalizing for no particular reason. And he generalized the notion of a cone like this. He says, oh, a cone, you no longer need to have an axis and a thing rotating around an axis to make a cone. Instead, pick any vertex point and any circle, and then just draw all the lines associated, you know, connecting any points to there. Whoop, now you have a cone. This is a more general definition of a cone. There, it gives rise to oblique cones that are not the kinds of cones that you get with the conic compass. These kinds of cones that, according to Euclid's definition, those are right cones. They have a symmetry axis like that, and that corresponds to you know, this axis could play the role of the axis arm of the conical compass, and that, you know, that fits very well. Now, if you generalize the notion of a cone like that, you're no longer in those kinds of cones no longer match up with the idea of the conic compass. So, okay, Apollonius seems to have sort of abandoned a little bit the constructed business. Very interestingly, when Apollonius sets out to construct conic sections, so basically, given the equation, draw the cone, draw the parabola, for example, right? This is a construction problem in the conics of Apollonius. Given the parameter of the equation and the location of the vertex point and the axis direction, construct the parabola. And it turns out from the proof that what Apollonius means by that is constructed the corresponding cone that would create that intersection. And he has a very elaborate construction about how to find the corresponding cone from those givens. And interestingly, he ends up giving the construction in terms of a right cone only. So the Euclid type cone, you know, he has generalized the notion of a cone, but when push comes to shove and he has to construct conic sections, he falls back on the old one again, the limited notion of cone, perhaps because he was thinking of the conic compass, perhaps, or, you know, so interestingly, the constructions of conic sections in Apollonius are in fact consistent with the conic compass interpretation of drawing cones after all. So Apollonius constructions are about finding this cone, and they are then, because they are right cones, those what Apollonius does can be interpreted as a way of configuring the conic compass so that it traces the parabola. So in other words, what Apollonius is doing, basically giving a recipe of how to set up the conical compass to draw the thing. You have to put the axis, you know, here's how you put the arm or the pen and all that stuff. So you can sort of read his construction as a recipe, as a conic compass recipe, and that is possible only because it's a right cone. Otherwise, it wouldn't have worked that way. This is kind of fun because of as you can see, also, for example, here he has this pointless scaling factor lambda. So once again, Apollonius is very obsessed with generality. You know, he's giving a very general construction that even includes an infinite family of cones, because the lambda is arbitrary, a scaling factor that you can pick. They all work and give the same cross section here. So even though he's so obsessed with generality and gives an infinite number of cones, even though only one would do, why don't you just pick lambda and be done with it? You know, lambda equals 1. You know, give a much simpler proof. No, it's got to be general. But nevertheless, despite his obsession with generality, he restricts himself to a right cone. He could have, of course, there are many other options with oblique cones. Those he skips, maybe because of the conic compass. Well, that's my hypothesis. So it's the same with the other constructions of a hyperbola and an ellipse. Always right cones in Apollonius. So the conic compass hypothesis, you know, here I'm just summarizing what I already said, that it solves a lot of mysteries, put a lot of things kind of fall into place if you allow this interpretation. It's in any case completely crazy. How are you supposed to solve construction problems by means of entities that are themselves not constructed, like conic sections, right? Surely, if you're going to solve the construction problems using conics, that entails that conics must be constructed somehow. And what could that construction be? Well, it has to be the conic compass is the only way to make sense of that in a way that is consistent with all the other constructions that everybody gave. So, well, that's my hypothesis then. In this way, I have constructivized, as it were, all the classical construction problems. It's all very coherent. Everything is physical, everything is constructed. So here I'm just sort of ranting a little bit against modern dogmas, you know. Today we have a backwards way of thinking about this. You say, oh, the more logical, the more pure, the more formal it is, oh, the more rigorous. And if you're doing something physical, this filthy stuff, you know. That can't be rigorous. That's the opposite of rigorous mathematics. You know, the Greeks, they were not stupid, and they had a different view of this. And the way they thought about it, pure logic, that's like philosophy, you know. We all know that mathematics is better than philosophy. This is how mathematicians feel today and have always felt also in antiquity. Pure theory, pure logic, this kind of stuff. You walk into contradictions and paradoxes all over the place. History shows. Russell's paradox, and where people make, you can't trust pure logic to be consistent. However, what you can do is to ground geometry in the physical, and that is in fact not at all that these people were interested in applications and they did constructions because of the physicality. It has something to do with applications or physics, or they were not doing pure mathematics. They were doing pure mathematics. They were doing more rigorous mathematics than us with their physical constructions. That's precisely the whole point of it, was to do pure theory. In fact, better theory than this. That was the way they looked at it. So all of that, modern prejudices have clouded the judgment about this and mistaken these things for sort of untheoretical, pre-theoretical, flimsy constructions. No. These people knew what they were doing. They were doing very sophisticated foundational work. Euclid was a Platonist. Here we see these people with their prejudices. The idea that Euclid was a Platonist, absolutely not. It's total gibberish. He was the opposite of a Platonist. It was precisely the grounding in the physical that gave mathematical certainty, precisely the opposite of these modern dogmas that have clouded everybody's understanding. Here's a classic argument for why Euclid was a Platonist. Oh, you just have to read the first two definitions of the elements, A point is that which has no part. A line is a length without breadth. That proves it. Lines and points are not physical things, because any physical line, of course, does have a breadth. So, gotcha. It's all Platonist, world of ideals or whatever. It's some kind of abstraction and has nothing to do with physical lines. That is a terrible argument, even though many people still fall for this trap, this fallacy. In fact, the idea of assuming that lines have no breadth and so on is done always in physics. In astronomy, we assume that planets are point without extension. We treat the moon as if it was a mathematical point. For example, Ptolemy does it all the time in the astronomy. Of course, he doesn't think that the moon literally has no part. You can tell that it's obviously not a mathematical point, but you treat it that. Archimedes treats the law of the lever, treating the lever arm as a line without breadth, of course, a negligible mass and so on. Look, if you do that all the time in any physical theory, obviously you cannot use that fact to infer that geometry cannot be physical. It's the opposite. Geometry is just as physical as astronomy, just as physical as mechanics, as statics. In fact, this idea that the line doesn't have breadth, you use it all the time in physical theories. So it's absurd to use that to say that therefore Euclid's geometry cannot be physical, in my opinion. So, well, okay, let me just end there, I suppose. By the way, I have you can find everything in this article here, all my arguments about this, if you like, more references and stuff. Okay, thank you very much. I'm happy to, if you have any thoughts or questions or objections, maybe, please let me know.
Thanks a lot. Let's thank the